All right, we're going to go over the second exam. We'll look at version B. A device used to measure the amount of heat absorbed or released by a chemical or physical process is a calorimeter. And there's different kinds of calorimeters, coffee cup, bomb, but that's what we use to measure heat from a chemical or physical process. All right, now we have a dilution question. Okay, there we go. Solutions made by diluting 25 milliliters of 12 molar HCl up to 500. So for this, we're going to do M1, V1 equals M2, V2. So we have our concentrated or our stock molarity, which is the 12 molar. We have the volume of that we used, which is 25 milliliters. You could rewrite this in liters if you want. We want to know the concentration of the new dilute solution. That's our M2, our variable, and we have the volume for that. There we go, 500 milliliters. So I'm just trying to solve for M2. 12 times 25 gives me 300, I guess, milliliters over divided by 500 milliliters. And in this case, M2 should equal a 0.6 molar solution. More dilute than the original, the 12 molar solution that we made makes sense. Which of the following would be considered a weak electrolyte? NaOH is a strong base, and when it goes into solution, it will dissociate 100% into those ions. KBr is an ionic compound, and when it dissolves in solution, 100% of it will dissociate into those ions. Then we have our acetic acid. This is a weak acid, and so something like 5% of them will dissociate into these ions, making that a weak electrolyte. And then the last one, the methanol, CH3OH, this is 100% covalent. It is not an acid or a base, so this is not an electrolyte. So that's why that was your correct answer there. The weak acid would be a weak electrolyte. Any reactant that's present in an amount greater than required by the reaction stoichiometry would be our excess reactant. So having more than we actually need is our excess. Having an amount that gets used up completely is our limiting reactant. How many moles of NO2 would be produced from, we've got this decomposition reaction here. And we have 5.8 moles of this. Now you may have had a different mole value, but the way you're going to do this is going to be the same. I'm going to use the reaction stoichiometry, or the ratio, in this case of one of the reactants to one of the products. And that's going to tell me how many moles of that product we'll make. We have a 4:2 or 2:1 ratio, so we'll have double the amount of that reactant. What would be the correct sign for a system doing work on the surroundings and losing heat to the surroundings? So if this is the system and it's doing work on the surroundings, that means it's losing or energy or putting energy into that in the form of work. So our W term would be some negative value, negative, X joules. And then if the system is losing heat to the surroundings as well, it's putting heat or thermal energy into the surroundings, then our Q term would also be some negative energy value. So the sign for both of those should be negative Q, negative W. What's the oxidizing agent in the following reaction? So I've got a zinc, a solid metal, I've got silver nitrate in solution, and then that goes over here and makes zinc. Oh, there we go. Sorry. Nitrate, or zinc 2 nitrate specifically, and then I've got two solid silvers over here. So free element by itself, 0. Got an ionic compound here. Silver would be a +1, oxygen a -2, nitrogen a +5. Over here, the zinc is a +2. The nitrogens are a +5. The oxygens are -2. And our silver now is an element in its natural or free element, no charge by itself. So if I look at zinc was oxidized, and if I look at silver, it was reduced. So the oxidizing agent is the thing that promotes oxidation. So as zinc is losing electrons, there has to be something there to take them. What's that going to be? Well, that's going to be the silver there. So the reactant that contains the element being reduced is our oxidizing agent. Determine the molarity of a solution formed by dissolving 3 moles of NaCl in enough water to yield 4 liters of solution. Molarity is just moles of solute over liters of solution. So if I do that, that will give me my molarity. Which of the following reactions would be considered acid-base? So here I have silver nitrate plus lithium chloride goes and gives me AgCl, which is now a solid, and lithium nitrate, which is aqueous like everything else. So this would be a precipitation reaction. Then we have zinc plus Cl2 goes to form zinc chloride. Neither one of these is an acid or a base, and I can actually see if I go over to here that the oxidation states of everything is changing. So this is a redox reaction. And the last one, we have perchloric acid reacting with sodium hydroxide. So I have an acid and I have a base. There's my acidic hydrogen. There's my OH. It gives me water and a salt. So that is my acid base reaction right there. What coefficient should go in front of the water when this is completely balanced? So I might look and say, I got 2 carbons on the left. What if I put a 2 in front of this? Now my carbons match, but now I have 3 oxygens. Oh, but my hydrogens, I have 6 hydrogens on the left and only 2 on the right. So maybe if I put a 3 in front of that, now my carbons match and my hydrogens match, but now I have 5 oxygens. So I could do 5 halves in front of this, and this would technically be balanced. Although I think I said using only whole numbers. So if I can get to here, if this kind of helps me, saying, hey, I have 5 halves of an O2, but then I want whole numbers, all I'm going to do is go through now and multiply everything through by 2. So if I multiply the one in front of this by 2, I get that. If I multiply 5 halves by 2, I get. If I multiply my 2 by 2, I get 4. And if I multiply my 3 here by 2, I'm going to get 6. So the coefficient in front of the water when this is balanced should have been 6. All right. Identify spectators in the following reaction. So I've got Na, which is aqueous. And I've got S2 and Fe2 plus, and then what, 2 NO3. Oop. And that goes to form FeS, which is a solid, and then I've got Na plus, or 2 of those still, aqueous, and 2 of my nitrates. Come on. Aqueous. So what I'm looking at is this is a precipitation reaction. I do have a solid on the product side. So I'm kind of concerned with what went into making that solid. So that would be the Fe ions and the sulfur ions, iron and sulfur. And then what didn't go into making that, or essentially what is unchanged. And that would be the sodium. There are 2 Na plus aqueous on the left side and the exact same thing on the right. And then also the nitrate. So my spectator ions would be the Na plus and the nitrate, the NO3 minus. All right, how much 0.15 molar KOH do I need to titrate 50 milliliters of H2SO4? So I've got an acid-base reaction. If I can't visualize it, I might want to write it out. There's my base part, there's my acid part. I'm going to make a salt. Sulfate has a 2 minus charge. So it looks like I have 2 acidic hydrogens. I need 2 potassiums. So it looks like this is going to react in a 1:2 ratio. 1 mole of acid for every 2 moles of base. Now we have enough information about the acid to figure out how many moles of that acid we have. We're given the molarity. It's 0.075 molar, which means there's 0.075 moles for every 1 liter of solution. I can multiply that by the volume. We had 50 milliliters or 0.05 liters. So when I do that, we get 0.00375 moles of our sulfuric acid. What we're concerned with is how much base we need. So we want to find out how many moles of base will it take to neutralize that much sulfuric acid. And we know that that's a 2:1 ratio. So I want 0.0075 moles of KOH. We're given the concentration of KOH, 0.150 molar. So if I take the number of moles that we need and I divide it by the molarity, I will get my volume, and that should be 0.05 liters or 50 milliliters. So it makes sense. If we need twice as much KOH, but it is twice the concentration, that it would be the same volume. All right, what precipitate would form between these two? So I have ammonium chloride and it's reacting with, there did we go? Potassium bromide. So I'm just going to swap. I'm going to take the positive portion of one and swap it over to the negative with the other and vice versa. If I do this, I would get ammonium bromide and I would get potassium chloride. You go to your solubility rules, you'll see that something with ammonium is always soluble. Bromides are typically soluble unless paired with a few things. Ammonium isn't one of them. And potassium is a group 1A metal, and those are always soluble. So everything starts as aqueous, it ends as aqueous. There's no net ionic reaction, so this would actually be no reaction, or there's no precipitate formed in this example. All right, reactions. We've got this reaction right here. Iron 3 oxide reacting with carbon monoxide and giving us 2 irons and 3 CO2s. And we're told that we started with 22.55 grams of this and 14.78 grams of that. And we want to know what's the limiting reaction. So the way I'm going to do this is find out how many moles of each of these I have and then compare them both to the same product. So for iron, I'm going to take that 22.55 grams and I'm going to divide by the molar mass of that, which should be the mass for 2 irons and 3 oxygens, 159.69 grams per mole. So that'll give us there we go. 0.1412 moles of that iron 3 oxide, and I want to multiply that by, we said compare it to one of the products. I'm going to use iron for both of them. You could use the CO2 instead if you want. In this instance, it's a 2-to-1 ratio, so that means it should make 0.2824 moles of iron. We're going to do the same for this carbon monoxide. 14.78 grams of that divided by its molar mass, 28 grams per mole. And we get 0.5278 moles of CO. And we're going to multiply that by the same ratio, or to the product, I'm sorry, to the same product, using the ratio of that product to this, which is 2/3, which gives us 0.3519 of iron. So what produces the least amount of product? The iron oxide, or the iron 3 oxide right there. It'll get used up first. The maximum amount of iron we can make is 0.2824 moles of iron. So that's our limiting reaction. Once it's used up, the other any further.